can we move on a little bit to some area where we may not completely agree?
Sure. Sounds like fun.
In our first episode with a proper guest, we have Kevin Buzzard here from the Imperial College in London, who is well known for many things, for his mathematical work, but for us in particular, interestingly, he worked a lot on the popularization of the Theorem Proving Software Lean, and also formalized a lot of high-hanging fruits and did a lot of groundwork concerning formal mathematics.
And we are very pleased to have Kevin Buzzard here, who is Professor for Mathematics at Imperial College. Hope I say everything right. And your specialty is arithmetic geometry. Is this correct, Kevin?
Yeah, I guess so, yeah.
Yeah.
I normally say the Langlands program now because it makes me sound fancier.
Oh, that's better. Yeah. If we know what it is. And you are, I would say, one of the leading advocates for using a lean proof assistant in mathematics, if I may say so.
Yes, that is probably true, yes. I've been banging on about it for years now.
Very good. And I should remark, Kevin, you pointed out that you're not a logician and you're not working in the foundations of mathematics, yeah. But we thought it's a good idea to invite you because actually proof assistants like lean are having a major impact on the role of logic in mathematics. So it's from this angle, I mean. And I think Dennis wanted to ask some basic questions.
Yeah, so maybe you could just start us with a very short introduction. What is lean? What's up with this natural number game? How can people start doing this or whatever this actually is? So
lean is an interactive theorem prover or a computer proof assistant. It's one of many, and it's a relatively new one. There are systems like Rock and Isabelle and others that have been around for much longer. And on the whole, these things were ignored by mathematicians. There was sort of a couple of exceptions, but somehow in the before 2017, you could count the number of mathematicians using any of these systems on the fingers of one hand. But for various reasons, I mean, one of which was me starting to bang on about them to various mathematicians. In the 2020s, somehow they've caught on a little bit more in the mainstream mathematical community. And now you do find lean courses are popping up in mathematics departments, or theorem prover courses, but mostly lean courses, which is something that is sort of quite surprising and quite exciting as far as I'm concerned, completely new. So that's how things have changed, and why they've changed. I mean, it's sort of a combination of various reasons, but I do think that the advent of sort of ChatGPT, which sort of hammered home the fact that AI was coming for everybody, including mathematicians, was at least something to do with it. Even though actually AI is, in some sense, nothing to do with interactive theorem provers. But the idea of getting AI to write the code instead of getting humans to write the code is one of the many things that's sort of powering the area at the minute, I think.
Yes, I mean,
I'd like to speak about.
Sorry, I'm always thinking it's like if you just have ChatGPT and may tell you all sorts of nonsense, but if you have a proof checker, you can actually check that this is okay, no?
Right. So that idea somehow, I think at the beginning that was quite naive, but actually this is really now becoming viable. At the beginning, ChatGPT was terrible at writing lean code, but actually people now have systems. There are language models which are getting very good at writing lean code. So, I'm certainly not suggesting that these things are going to start proving new theorems all by themselves, at least not in my area. But I do wonder whether we're getting to the point where sort of translation of the human literature is something that might be becoming more viable, although it's still a fair way off. And that would be a very interesting development. Because our literature is written by humans, and so it's got mistakes in. And if we could get the thing to referee mathematics papers, that would be a big win.
Yes.
So
So Dennis, you were going to ask something?
I just wanted to say I like to call this good old-fashioned AI in order to keep attractive for grants. So we also can use AI doing logic. I mean, it's slightly different AI, but as long as nobody knows. And I mean, there were quite a few successful stunts involving formalization recently, right? Research level math has been formalized. The liquid tensor experiment. There's another one. I only have the book in German. Can you think what I'm hinting at?
Yeah. So I'm,
I mean, it's not done yet. Yeah.
I will be absolutely honest. So in 2017, I got interested in these things for various reasons. And I have been behind, several things that I think it would be fair to call them stunts. They were genuine mathematical projects involving formalizing mathematics. The way these things work is that they can't necessarily do much mathematics autonomously, but they can check mathematics if you type it in. And I was specifically targeting mathematics that I thought would get the mathematics community excited, and trying to type this stuff in. And I was completely open. Our paper, the first stunt really was formalizing the definition of a perfectoid space, and this was something that won Peter Scholzer the Fields Medal in 2018, and we did this. We finished in 2019. And it was really nothing more. I mean, it did take a long time to do because we needed a lot of foundations. We had to build up a lot of, topology and topological algebra. But me and Patrick Massot from Paris-Saclay and Johan Kommerlin, who was then a postdoc in Freiburg, the three of us, we sort of typed in this definition of this thing that had, everybody was on everybody's lips because Scholzer had just won a Fields Medal. And at the end of it, it was nothing. We didn't prove any theorems about this object. And we couldn't even, no, it was worse than that. We couldn't even construct any examples other than the empty type. We proved that the empty set was a perfectoid space. That was our big theorem.
Oh.
And the computer scientists were, I think, looking at us in some bemusement because they could see through the work in some sense. But the mathematicians who had far less understanding of the area were just saying things like, "Oh, we had no idea that that computers were so advanced now." Somehow it was there was a real sort of a lack of comprehension, which we could absolutely see coming because mathematicians were not really engaged in the software at all. So one person that did see through it was Scholzer. He knew that we'd done nothing in some sense. But he could also understand what we had done, which was sort of developed a system that sort of was beginning to understand, what we were teaching the undergraduates. That was the thing. That was what I found in 2017. I couldn't really find a system that had one coherent exposition of all the mathematics that we were teaching to the undergraduates. Even though computer scientists would say things like, "Oh, I'm sure that must have been done by now." But I could always list like 5 things that I was taught as an undergraduate, and that no system had been formalized in no system at all. So when Scholzer realized what was going on, he said, "Okay, why don't you prove one of my theorems? Not a theorem about perfectoid spaces, but why don't you prove some theorem in the theory of liquid modules, which he'd just invented with Clausen." And he specifically chose this because he could see that the main argument was just a very long undergraduate level argument. It was very technical and messy, but the point is that the objects it used were only undergraduate level. And so we could see that this was a feasible project. Whereas if he'd just said, "Why don't you prove one of my theorems about perfectoid spaces?" this would have been like a decade long, it would have been completely ridiculous. This would have needed funding. So that was the story of the liquid tensor experiment. We proved this main theorem about liquid vector spaces. And again, you could argue that this was also a publicity stunt in some sense, because it was just 10 pages of undergraduate level material. But on the other hand, Scholzer was arguing that nobody had actually ever read it. And that was how the project started. Scholzer emailed me and said, "Did you have a study group on this, on this course I'm teaching in Bonn?" And I said, "Yes. Me and some other people at Imperial had met once a week and sort of read through the notes. And then he specifically said, did you read the proof of theorem? I think it was 9.4. And I looked at it and said, no, we just skipped that. And he said, yeah, everybody says that. Everyone is skipping this proof. And if this proof is wrong, this is the lot of the Fields medalists. Voevodsky pointed this out, right? Once you're sufficiently esteemed, like nobody reads your proofs anymore because everyone knows you're a genius, so we don't need to check the details anymore. And for Voevodsky, this was a problem because something he published was false.
Yes.
So Scholze didn't want to go down the same route. So we proved this thing, and then Scholze started saying, it's incredible that these systems have got this far. And then, of course, things suddenly started appearing in the mathematical, the media like Quanta and Nature, and that was it.
And turns Tau is using Lean as well, no?
Right. So by that point, my job was done when that happened. There was a conference in IPAM in 2022, a much broader conference about sort of modern uses of machines and in mathematics. And I was one of the organizers, and so was Tao, and I invited a lot of Lean people to speak. So just sort of put them in front of him, and they showed the things that were happening in the system, and it just piqued his interest enough. It made him realize that the system existed. But then I think what my guess is that the key thing that happened was that he had a 2-page paper up on the archive answering a question that somebody had asked on Math Overflow. And he thought he'd learn Lean by translating this short, self-contained paper on inequalities into Lean. And then at some point, the system pointed out that he'd divided by 0, which you can do in Lean. You can do in these systems typically. You get a junk value, but in regular maths, you're not supposed to do that. And so. So there's another example. This 2-page paper was up on the archive, and everyone's saying, "Oh, Terry Tao's given this cute answer to this question." But again, who's actually read it? Like, it turns out at some point he's divided by some number which could sometimes be 0. And so then he's fixed it, and then of course you have to change some of the constants, and the main theorem's suddenly a bit different. And then the next thing he's proved a big conjecture, the polynomial Freiman-Rüge conjecture. And announced that he was going to formalize that. So suddenly you have an opportunity to collaborate with Terry Tao if you understand some Lean. And 3 weeks later, the whole thing was done. This 35-page paper got formalized before it had even been sent
to get more people involved, right? Doing parts of the proof.
Out. Right. He broke it up into small pieces. And then anyone could get involved. I mean, there's a computer scientist I know in Brown, Rob Lewis, who would certainly not say he was a mathematician, but he wrote the linearith. He wrote the Fourier-Motzkin elimination tactic for Lean, which solves inequalities. And he noticed that one of these tasks that Tao had given was just solving an inequality, and so he sort of did a drive-by PR, and it was just like, this is great. I'm suddenly collaborating with the Fields medalist. He actually did another one of the publicity stunts, if you like, earlier. In 2019, when I was doing perfectoid spaces, he formalized an annals paper, a 2017 annals paper. So this is widely regarded as the top pure maths journal. But he found a specific paper that was, sort of quite short and relied on very little, and managed to formalize the entire thing. A theorem by Ellenberg and Gijsweit on this, some generalization of this game set. Is a combinatorial question. A lot. Of course, once Tao is involved, then my job is done. I no longer need to promote this software because he has a far wider reach than me.
But you've got a project on this to formalize this Fermat proof, right?
Right.
And how is this?
So again, that's part publicity stunt because that sort of seems like a high profile thing. But again, there is a genuine reason. All of these things. There's content here, and there is a reason. And the reason is, in 2018, I was whinging that none of the systems had an undergraduate degree, but now we've essentially got an undergraduate degree. We've got most of it. There's still a couple of things I can put my finger on that I was taught as an undergraduate and are not in the system. For example, Theorem cohomology, just some buzzword. I learned this in third year manifolds. But now I'm aiming higher. I want these things to understand what's actually happening, across mathematics, and what's happening in modern, in a mathematics department. Why shouldn't the system be able to understand that? We can understand perfectoid spaces, so in theory it can understand anything. But right now, I go to the number theory seminar every week in London, and the question I always show up asking is, can we actually state the main theorem of this seminar in lean? And as often as not, probably more often than not, the answer is no. We don't have the machinery
because you
to
don't have
state
the
these
libraries
things.
yet.
We just don't have the definitions.
Mm-hmm.
So the point of doing Fermat's last theorem is, I just thought it would be Fermat's last. Wiles didn't just prove Fermat's last theorem in the mid-90s. He introduced a bunch of important new techniques that are still being used today, and they've been generalized and simplified, and the language that he was using is still absolutely being used today. And so I just thought, if we've got an excuse, to formalize Fermat's last theorem, why not? It's a target. I mean, it's an extremely difficult target, but the real benefit is that along the way we're going to be forced to formalize a bunch of definitions in mathematics, which are being used today. But it's really a bunch of definitions in number theory which are being used today, and somehow actually since then, my vision has got even broader, and I've just been funded by Renaissance Philanthropy to hire 4 postdocs whose job it's going to be to formalize the statements of recent papers in the Annals of Mathematics and other top pure journals, across the board, not just in number theory. I've hired people from across all areas of mathematics.
Cool.
So this is where I see the thing going now. Let's actually teach the systems what we're talking about in 2025, because this is the thing that the mathematicians have responded to. This is the thing that wasn't really happening in the 2010s. I mean, people were doing highly non-trivial things with these systems. There's the 4-color theorem and the odd order theorem. The big results proved in rock, really non-trivial things. But somehow they weren't sort of cutting edge stuff. In rock, they're like, we've done the odd order theorem. This is like a 300. This to me was proof that these systems have got good, right? They can handle a 300-page proof. Then they've got really good. But the mathematicians look at it and say, well, that was it's the results from the 70s. Like, who cares about that? It's ancient stuff. This is where the manipulation comes in. Right. This is why you have to do publicity stunts. This is why me forming formalizing the definition of a perfectoid space. This is nothing compared to what Gontio was doing in rock, 10 years ago. But that was what got the mathematicians excited, because it was something that happened, the year before. That was sort of the insight, really. Try and get to the boundary in whatever way possible, because that's what will make people excited.
Cool. Can we move on a little bit to some area where we may not completely agree?
Sure. Sounds like fun.
You said that you grew up using ZFC and predicate logic as a foundation.
I did.
And now you use a system which is based on type theory. How do you feel about this? Is type theory better suited, maybe for formalization, maybe for doing math in general?
I mean, it's going to be difficult to convince the mathematicians that the mathematicians, they say they're doing, I mean, they're not really working in ZFC, right? They're doing mathematics. They're doing what Gauss and Euler and Riemann were doing, who were doing non-trivial mathematics before the axioms existed. So that's what mathematicians are doing now. They're doing mathematics. But for some reason in our community, the set theorists won. The set theorists, and now people say a group is a set equipped with an operation and blah, blah, blah. They say this word, even though, if you put a gun to their head and ask them what the definition of a set was, who knows what they would say. But
I mean, so
and
in a
you know,
way, sets and types are almost sort of can be interchanged in a way, right?
yeah, at this level, yeah. So in Lean, we say a group is a type equipped with a multiplication and blah blah blah. But at the end of the day, what we really want to say is, you know, a group is a collection of stuff, right? You know, a group is a collection of stuff, and you can multiply the stuff together, because that's the idea. And a set and a type are both completely, in some sense, completely different ways of capturing this concept of a collection of stuff. But, you know, a group is not a set equipped with a multiplication or a type equipped with a multiplication, because Galois invented group theory in the 1820s or something, the 1840s. Whereas, like, the concept of a set wasn't invented until, you know, sort of 40 years later.
Yeah, I mean, obviously,
so, you know, whatever Galois said a group was, he certainly didn't say it was a set. Right?
Yeah, that's perfectly valid. I mean, that there is, even when we do mathematics, I mean, we first think in a sort of semi-formal or informal way and explain things. Yeah, but then and I think, trying to formalize it, if you want to do the step, you have to be sort of precise, and actually also before, I think in mathematics there were sort of arguments on what does it actually mean, or what is the foundation. So this is a development, right? That foundations were made more precise, right? And there's the attention between sets and types, right? Because
they are different, even though I don't tell anybody that, right?
Yeah. Okay, maybe it's better for selling. It's better. I tell my students, I say, I teach logic, using Lean actually, and I say, and here are some types and sets on your pay grade, they're the same.
Yeah. That's a great way to put it, I think. And I didn't really realize this. I mean, it took me a while personally to come to this understanding that actually every time I use a set, what I either mean a type or I mean a subset.
Yeah, exactly.
And in my mental model of what was going on, those were the same thing.
Yeah.
You know, I mean a subset of some fixed universe. But in Lean's way of formalizing, these are different things. There's a type and there's a subset. You know, a subset is a term. And it took me a while to convince myself that actually saying you're not allowed sets, you're allowed types and you're allowed subsets, and that's it.
Yes.
It took me a while to convince myself that actually that was enough.
Yeah.
That was it. That was, you could absolutely do mathematics, because my memory of what a group is somehow a group is like some ordered four tuple consisting of completely different objects. You know, there's a set, which is the underlying set, and then there's a function, and you know. And so in my mind, it was really important to have these very crazy sets whose elements belonged in different places. You know, and in Lean you can't do that. You can only have a subset of a type, and somehow the type is like homogeneous. But when I realized that you didn't have to define a group to be an ordered four tuple. There were other ways of defining groups. You just have to collect that data somehow, and it doesn't matter that the objects that you're collecting together are of different nature. You know, one of them is the underlying set, and one of them is a function. You know, one of them is an element of the set because it's the identity. You could put these things together without having to, without having exactly. And then there's propositions, and by making sort of these structures that you can do in type theory, you can just sort of bundle everything together, and it doesn't matter that these things are of a different nature. That was somewhere when it all dawned on me that that my mental model could be adapted, and I could still do all of the things that I've been doing for the last 30 years as a research mathematician.
And in a bit more disciplined way, I would say, because I mean, otherwise you can always ask, what is the union of two sets, and that's a weird thing. And what's the union of the set of groups and the set of whatever integers? This is a confusion.
Yeah. But mathematicians have always been vague about this.
I know. Yeah.
But somehow, another thing that dawned on me was that actually these things don't matter. It's very easy to ask weird questions.
Yes.
And what was, I think, quite shocking to me at the time when I was learning this stuff was you could ask if the natural numbers are equal to the integers. Like this question is not, there's a mathematical answer to that, which is like no, because -1 is an integer but not a natural. And then there's the foundation person's answer to this question, which suddenly is firstly A, not that answer, and B, completely different depending on what foundations you're using. For example, in Lean, this question is undecidable.
It doesn't make sense.
It's a meaningless question.
Okay, actually, in hot you could ask this question.
And,
And the answer would be yes.
The answer would be yes. They're equal in lots of different ways, right?
Yes, but also
there would be many terms of type naturals equals integers.
No. I mean, what you would say is nat is equal to integers, but only as a type, or as a bare type, right?
Right.
If you don't know anything else, then all you can see is how many elements are there, right?
Right.
But if you have a type with some structure, algebraic structure, then they're not equal.
Yeah, then they're not equal.
I find this is not just from a foundational point of view, but also when you teach somebody, right? That is a more satisfying answer in a way. I mean,
I know you like that answer, but my experience when talking to mathematicians is if you tell them that the question is the naturals equal to the integers has got any depth in it whatsoever, and you could find models, there are models when it's true and there are models when it's undecidable, and they're just their eyes are glazing over because the naturals are not equal to the integers because -1 is an integer, but it's not a natural.
Yeah, but
as far as a mathematician is concerned, that's the end of the story.
Yes,
and
because
this question is completely. It must be pathological. This is a very unproductive line of argument when talking to mathematicians.
First of all, I wouldn't talk of models or something. I'm talking about this very naive conception of what these things are. Yeah, not models, nothing sophisticated. Yeah. But this is exactly the difference between types and sets here. I mean, if you think about sets, then obviously natural numbers and integers, are.
You say it's obvious, but it very much depends
depending on the encoding. Yeah. Actually, so in set theory, it's a difficult question, yeah. But
I can think of an encoding that makes it true, right?
Exactly,
I'm sure.
Exactly. It's just 0 is 1, 1 is -1, and so on. Yeah. So you can do this. But the answer in type theory, I think it's very clear, because if I give you a type, I give you a type here. Okay, only here I give you interest. So what can you do with it? Yeah. You can only look at the elements. There's nothing else. You have no addition. -1 doesn't exist.
Right,
it's
exactly.
just a type of integer.
The mathematician,
It just doesn't mean anything.
No, I absolutely agree.
Yeah. So I find this not a sophisticated question, but a question really even for the beginner to understand what things mean, because that's where they get confused. Yeah.
But you see, I'm going to say that it's not a mathematical question.
Sure.
In the sense that you cannot get a mathematician interested in this question because they dismiss the question as ridiculous. Right? I've told you the answer already.
Yeah.
The naturals are not equal to the integers because -1 is an integer and it's not a natural.
But this is
any further conversation that I know you're desperate to have, any further conversation is just not of interest. Like it's just not mathematics. We have to talk about other things. And I've spent a lot of time. We build API. In MathLib, in Lean's maths library, exactly hiding all of these weird questions from the mathematicians, because we know that the mathematicians are terrified by them. They know that the naturals are not equal to the integers, but they have no idea what the naturals are. They know they satisfy Peano's axioms,
Kevin,
but they don't know what they're made of.
But I wonder whether this idea...
And they don't care. It doesn't matter what they're made of.
Okay, fair enough. I think the point where people care is when they learn concepts, right? And I know there's lots of confusion if you talk to students, who try to make consistent picture, and then as you say, and then you discover ZFC and everything can be reduced. So this is a process of a certain brainwashing. Once you do this, then you're not interested in this question anymore. But I think it's
that's my job, is to brainwash the students to stop thinking about what a natural number actually is.
Why is this?
Because all you need to know about the natural numbers is Peano's axioms, right? And any further questions about the actual nature of the natural numbers are irrelevant from a mathematical point of view. Obviously, they're very important from a foundational point of view, because if you make a foundation, then you've got to figure out how to make the naturals in those foundations. So now you do have to figure out how to make 37. But as a mathematician, I start at Peano's axioms.
But you're saying, as a mathematician who has already gone through the process of brainwashing, I do this, and the other mathematicians, the culture of mathematicians, does it the same way, and I find it, and it's not because of some highbrow philosophy, but very low level. I mean, people ask these questions, and I think it's good for people to ask these questions. I think
some people do, yeah.
I mean, no, but students usually ask these questions, and then they get sort of brainwashed, I would say, in one way or the other. So I think there is an interest in also for people who are not mathematicians, who are members of the public, who also wonder about the weirdest things, to be able to explain, obviously, to explain mathematics and to explain the idea. I think it's important to also deal with these questions.
Do you, I mean, is that true? Right, that's the thing. I wrote this game, the natural number game, to teach students at Imperial. Initially, it was a part of our first year undergraduate course, but it presents Peano's axioms as God-given, and it makes no attempt to ask the question what actually is going on under the hood. Right? It hides it, and that's why. That's why. Here's a story. When I was a first-year undergraduate, in my first week at university, I was told that we were going to be studying the real numbers in our first-year analysis course. And we were given the axioms of the real numbers, including this least upper bound axiom. Any non-empty bounded set of real numbers has got a least upper bound. And we were told that it characterized the real numbers, and we went on from there. And we weren't even given
Cauchy
a description of... No, Cauchy, Dedekind, nothing mentioned. We were just told the real numbers satisfy these properties, and now let's build calculus. Yeah, and 8 weeks later, we'd got the definition of the Riemann integral. We had definitions of differentiation and integration, and we proved the big theorem that if you integrate and differentiate, you get back to where you started. And at no point did anybody ask the question, what actually is the real number 2? And the even weirder question, is it equal to the natural number 2? Right? Weird questions like that. And you could ask, well, what are the real numbers? And then, your supervisor would just say, well, you can make them with Cauchy sequences, you can make them with Dedekind cuts, and nobody cares. And you really get the impression, like, there's multiple answers to the question, what is pi? But none of those answers are of any relevance to what we're actually doing, which is developing the theory of calculus. So there's very much a line drawn in mathematics departments where you say, here's the, don't open the box. Here's the box. Don't open the box. Here's the axioms. Off we go.
So I must just do this short advertisement. If you want to open the box, there are still philosophy departments, and those people love to think about exactly that.
There's people like Thorsten. There's people studying time.
Philosophy is almost a dirty word in mathematics, right?
In math, it is.
As soon as
and I think set theory suffered from that.
If you say philosophy,
perceived as philosophy-ish.
Yes, if you say philosophy or logic and shit. Why do we need logic? We can reason. No, I mean, this is an observation that philosophy. I think also in my mind has a lot of to do. If I hear philosophers of mathematics, and I include everybody present here, but sometimes I find they talk lots of not very well informed stuff. Even me as a sort of not very, I'm not a mathematician, a computer scientist, but even me, I find that they often get the wrong end of the stick, and so they get this impression on the mathematicians that these are people who don't really know what they're talking about, and if anybody says philosophy, they say, this is just, I'm not interested, but I do think, and I don't agree with you, but okay, I'm not working in a mathematics department. Abstraction is important. At some point, it's important to say, okay, let's forget about the definition and let's work abstractly. I mean, that's a very inherent in type theory in a way, that you don't look as how things are defined, but also what the interface is to the rest of the world.
Yes, I found this a very beautiful way of doing mathematics, about really isolating the universal property. That really comes in early in type theory.
Yeah.
And I did find it a very beautiful idea as a mathematician. But somehow, opening the box is something we don't need to do.
I'm not sure, because I think by teaching people lean, in some sense, you cannot avoid opening the box. I mean,
no, I absolutely disagree. I teach students. My students have no idea what the definition of the real numbers is, because my students have access to all the axioms that I was told. Right, all those things have got names in Lean's maths library, and we know that you can develop calculus from those axioms. So we just give them access to the axioms, and then, I mean, this is how we teach the course. We say, find something you learned as a first-year undergraduate. That's their first project. Find something you learned as a first-year undergraduate, and then prove it in Lean. And they only need to know, the axioms that I was given, because they were given the same axioms, and they can solve that problem. They never need to unfold the definition of a real number. Okay. And I would indeed strongly encourage them not to unfold that definition, because they're not going to like what they see.
I'm just saying, actually, in type theory, if you replace one definition with a isomorphic definition, you will be able to prove all the same theorems, right? Which is not true in set theory.
I mean, well, it is true in set theory, but we would have to make a machine to do it. I see. So strictly speaking, it's right. You could prove all the same mathematically meaningful theorems.
Yeah, but how? What's the meaning of mathematically meaningful theorems, right?
It doesn't open the box.
Yeah, but
that's the meaning. Right?
The point is, in type theory, you simply cannot open the box. Yeah. In set theory, you could be naughty and open the box. Yeah.
Right.
So
I understand this a lot more than I used to. I mean, I no understand. There's some question about, I have a question on Math Overflow where I'm saying, look, we've got these two different definitions of the real numbers. Like there's Cauchys and there's Dedekind's. I mean, there's Bourbach. I mean, there's plenty of definitions. But I don't actually get it. If I prove these theorems about the real numbers, how do I know if I have some formal proof about, how do I know that I didn't open if I didn't open the box in the statement, how do I know that I didn't open the box in the proof? And does that matter if I open the box? I was very, very unclear about how these things worked. And then, of course, some people that were much wiser than me explained that everything was fine, and, I didn't have to start worrying about what was in the box. So
there's also the hot definition.
It's very beautiful.
The hot definition is that the reals are the Cauchy computation of the rationals.
No, that's Bourbach's definition. The uniform space completion of the rationals.
Yeah. But the nice thing of this is that this avoids using the countplex of choice. But anyway, let's not go there.
I mean, it also avoids using metric spaces. We're normally taught, we have this circular argument, right? In second year, we're taught metric spaces, and these are sets, as we tell these students, equipped with a distance function, which is real values. And then we teach the concept of a complete metric space and how you can complete a metric space. And then we say, oh, and of course, now actually this fills in a gap that we didn't do in first year, right? Because in first year, we didn't open the box, but now we can open the box and we can just we can now give a definition of the real numbers. We can define it to be the metric space completion of the rational numbers. And you kind of think, oh, that's great. That's sorted out all those problems. But then your definition of metric space has got the real numbers in it because it's real valued. So there's this circular thing that slipped past me, and I didn't spot this thing at the time. And it's only later you're thinking, wait a minute. I asked Imre Leader, my supervisor at the time, and somebody who was extremely wise and also 7 years older than me, so I'd sort of run into these things already. And he said, yeah, you've got to first make some crappy metric space definition that only involves the rational numbers and just do rational distances, and you can get away with it, but you have to give two definitions of metric space. And I was just like, oh, okay, so that's how it works. And it was only much later that I learned the concept of a uniform space.
Actually, which is the definition
and then you can complete the uniform space.
The definition in hot is mutually. I mean, you define the set or the type and the order relation at the same time, and you can do this. This is called a quotient inductive type. Maybe you cannot do this in in lean actually. So this is something which you can do in hot, but where you mutually define the two things, and then you have no cyclicity. I mean, the cyclicity is just, it's an inductive definition.
Right, because it's all happening at once.
Yeah.
So I'm always slightly scared by these definitions.
Oh, yeah.
In my mind, the beautiful definition of the real numbers is first build the rationals, and then prove it's a group, and then give it a topology coming from the order, and then use the addition to give it a uniform space structure, and then develop the theory of completion of uniform spaces. This would be the Bourbaki approach to mathematics, and so. And in Lean's maths library, we tried to follow Bourbaki, who wrote, of course, a car crash of an exposition on set theory, which they then proceeded to ignore all the rest of their volumes, and is now typically,
nice notation
in the set theory. I think mathematicians now typically avoid it and suggest to students they avoid it as well. I think that the logicians have got better ways to develop mathematics from the ground up. But from the moment they start doing algebra, they have a really excellent, second to none, their exposition. They do all the things that taught them to saying, find the right abstractions. They invented the concept of a filter when they were trying to figure out how to do limits correctly. So this is something we've very much been inspired by in the Lean mathematics community.
So if we close the box for a moment, and let me still ask very naively, having never really formalized something. I mean, as a mathematician, I'm quite productively ambiguous. So maybe my theorem is wrong for the empty graph, and I don't care, because who cares about the empty graph, right? But if it works out in every interesting case, but the edge cases, then I say, I didn't meant the edge cases. But after
exactly.
The fact,
you can change the statement of the theorem later and say, obviously,
slightly. And there's a lot of this and cheating, and sometimes the definition includes the zero, sometimes it doesn't. But you cannot cheat like that when you formalize something, right? Is that a real problem, or is that just not?
No,
happening?
It's just mathematicians are just annoyed. They know how to deal with the edge cases. They're just lazy. They're not ignorant. They're just lazy, and then this forces them to not be lazy. So hard.
And if you iterate that, so to speak, so if you switch between two definitions in your everyday math life, it's fine. But in your formal mathematician life,
you're only allowed you need one definition, and then you want to prove a theorem saying it's the same as the other definition.
I mean, there's also mistakes coming in because exactly of this, right? So that you use two definitions.
Yeah? Oh, yeah. My favorite one is this standard proof that the square root of 2 is irrational. Where there's this key intermediate, you assume it's rational and you clear denominators, and then there's this key intermediate step where you say, well, now m is an integer or natural, whatever you like, and m is an integer, and you say m squared is even, therefore m is even. And this is the hardest step in the proof, I think. When you say to undergraduates, how do you justify that? They can write all sorts of rubbish, and then eventually someone has the brilliant idea that you prove the contrapositive. Instead you prove that if m is odd, then m squared is odd. And this is apparently the contrapositive. And then you say, well, how do you prove that? And they say, well, this is obvious, because every odd number is the form 2n plus 1. And then you square that and you get even number plus, so, but this argument is flawed, right? This is logically flawed, because when you do the contrapositive, your definition of odd is necessarily not even. And when you do the algebra, your definition of odd is of the form 2n plus 1. So you have to prove the theorem that says every integer which isn't of the form 2n is of the form 2n plus 1. And this has some content. You do this by induction or something like this. And this is something I never noticed. I'd taught that proof, I'd learned that proof, I'd seen that proof so many times. And then when I formalized it in Lean, I was just like, oh, what? Wait, what? Like, I had to factor out some subnumber. I just never noted, because I've got two different definitions of even in my head. One of them is not odd, and the other one is of the form 2n plus 1. And everyone knows that they're the same. As a child, I knew these were the same. Obvious, And like my mother's a primary school teacher. She knows that they're the same, but I don't think she knows what induction is. I think she's probably long forgotten if she ever knew.
Yeah. Okay.
And in general, like, how close can you stick to I mean, you talked about translating human proofs. How closely can you stick normally to a regular proof text? How
Yeah, it's
big are
fine.
the
You just have to
guesses?
add.
Is
You
it?
just have to add more details.
Right.
It's just a chore. You know, maybe the machines will get good at doing it. You know, this is something that I'm very open-minded about, but I can sort of see a path to that. You know, I can't see a path to machines proving the Riemann hypothesis yet, but I can see a path to machines doing translation. But this is the thing they'll have to get good at. They've got to they read line n, and then they read line n+1, which says clearly this follows from line n. And now the language model has got to start generating text, which explains why this is clear, and then attempting to translate it into a system like Lean, which will then justify it. And whether in practice this is a step too far for the language models, because humans skip a lot of steps. But this is as a mathematician, I've always been very careful. I've been reading papers, and I'm constantly thinking, can I translate this back down to the axioms of mathematics? You know, this is how I was trained to think very carefully. You know, not everybody thinks like that, but I was, you know, trained to check all these fiddly details and like don't just skip it and say, well, it must be true because the reader says, you know, just the writer says it. Just check everything. So I'm quite practiced to sort of mentally filling in these careful details. So all that's happening now is I'm being forced to fill them in. But as I say, this is, in my mind, this is a correct part of the process. So yeah, it's hard work, but yeah, but as I say, it's also I find it extremely satisfying. This is one of the. I'm sure, Torsten, you feel the same. It's very, very satisfying doing mathematics in these computer systems.
Yeah. It also helps you to structure your thoughts. I find. I mean,
it
it's
makes
not,
you think clearly.
It's not just a burden, as Dennis just points out, but it's actually also helpful. Even if I don't want to prove everything, if I just start to write the definitions in a sort of typesetting in a formal style, then it helps me to structure my thoughts. So I've just experienced it's a positive thing. I mean, yes, there is this extra demand for discipline using a system whether it's Lean or whatever, but there's also payback in terms of the ability to structure your thoughts. In a bit, yeah.
So in fact, to my surprise, quite recently, have we got time for Fermat's last theorem story?
Yeah,
sure.
Which is very much
there's always time.
It's new. It's new. It's recent, and I found it quite surprising, and it very much, you know, amplifies what Torsten is saying. So I've been a year into proving Fermat's last theorem, and I spent the first year doing a lot of stuff from the bottom up, you know, working on sort of basic definitions that were sort of missing, and that we couldn't even state some of the interesting theorems until these definitions were made. And about a month ago, I switched and I started working top down. So I was, you know, stating some very abstract, you know, complicated mathematical results, which sort of put together would prove Fermat's last. You know, I was breaking down the proof into complicated, but short. I was breaking down the proof into smaller parts, and during this time, I found one abstraction, which I hadn't really noticed before, the concept of a hardly ramified Galois representation, which is a new concept that somehow Taylor and I have come up with, and is just the right abstraction to make a lot of these statements very, very clean. You see some statements where the statement of the theorem is very complicated, and these statements that we're writing down right now are very, very clean. You know, a mod p hardly ramified representation lifts to a p-adic hardly ramified representation, and a p-adic hardly ramified representation spreads out into a compatible family. And these statements are very, very short in Lean because we found the right abstraction. And then the other really weird thing was that we were trying to work out the class of rings R for which our theorem should be applied to. And there's all sorts of sort of suggestions in the literature. There's complete Noetherian rings and there's pseudo-compact rings, and some people arguing that this class of rings is too small and arguments would be easier if they were bigger, and there's profinite rings and all these other things. And then a PhD student of mine last week just pointed out that the correct answer is that we should be considering compact Hausdorff rings. And these are two really, really basic concepts in topology. And he showed me this proof that a compact Hausdorff ring had all these other properties that I had no idea that compact Hausdorff rings had. And so again, we have the statement, our target rings, this target category is simply the category of compact Hausdorff rings. And I've never really seen this category being studied before. And it's taken a long time for the penny to drop. But that's what everybody was working. In fact, many people were working with this category without even noticing, let's take our profinite rings, such that the topology is generated by translates of open ideals. It's just like, this is a really messy category, but we can work with it. And then it's just dawned on me now that it's the same as a very, very clean category. So the process of formalization is making the proof of Fermat's last theorem better, I would strongly argue.
Yes.
So it's not just at the basics, it's absolutely happening across mathematics when you're forced to formalize things, because you need to make the stuff as simple as possible, because it just makes your life easier to have simple statements. And so you're forced into thinking what the statement should be. And as I say, twice in the last month, I've been quite surprised that somehow things are coming out much more cleanly than I was expecting. I thought the intermediate statements would be messy, but actually they're just as beautiful.
Excellent.
That's lovely. Back and forth, both sides are winning. The formal side and
Yeah.
the
So
informal one.
everybody is winning. Yeah, I'm telling mathematicians who have no interest in the formalization how to tidy up the literature.
That's great.
Okay.
So
Yes,
we should
you
say
want to-
thank you for spending your time. And if you want to have anything to say, I mean, we haven't touched on so many things.
It's lovely to have a
Very-
chat.
Very good. Thank you very much. Yeah, it was
Great.
very, very interesting. Okay.
Great. We will link the natural number game below and
Great.
see you around.
Okay.
Yeah.
Bye bye.
Oh, great. I hope there's enough stuff you can use.
Yeah, sure.
Sure. Okay.
Okay.
So this was another interview at About Logic. I hope you had fun. You can engage with other people in the commentaries below and subscribe and get the bell or something like that in order to get notification whenever the next interview comes up. So I hope to see you all around. And if you have questions we should ask, suggestions for people, do not hesitate to comment.